This is 8C, an introduction to moments and center of mass. Now that we need total mass, now we're going to move to the idea of moment. From that we can calculate the center of mass. The way I think of these problems, is I look at a comparison between work and torque. Work and torque are not the same things, but they have quite a bit in common. Here's the expression for work, which you might remember from a couple lectures ago. Okay, work is force, the dot product of force and distance, which is force times distance times the cosine of theta. That would be the cosine of the angle between the displacement and the force. So what we're talking about here is an object starting here and moving some distance d. And here's the applied force. Now, when we think of a torque, what we're thinking of is the rotation of the object, not the linear translation of the object, but the rotation of the object about some point. So here is a fixed point F. Here is the distance to the point where I'm going to apply the force. This will cause, if this is a solid object, it will cause it to rotate. The torque is F cross D, which is the magnitude of F times D, the distance from the application of force to a fixed point or a certain point along the object, times the sine of theta. If they're at right angles, this is just F times D. This torque causes the object to rotate, just like this force in this calculation is causing the object to translate. Now I'm going to expand this expression right here, and from that I will find the expression for the moment. Here's another kind of a picture of what I was talking about with the torque. This end is fixed. Here is the distance from the end of the wrench where I'm applying this particular force. Okay, so the torque about this fixed point is the force times the distance. And we're going to use force equals mass times acceleration. Well, particularly it's mass times acceleration due to gravity, whatever, mass times acceleration. Okay. The teeter-totter is the same principle. You have some balance point here, and the mass here is a force, and say you have a itty-bitty mass here, and there's a little force here. The torque, due to this mass, has to do with this distance. If this is mass 1 and it's big, and here's distance 1, here's little mass 2 and distance 2, then the total torque on the system is the sum of these. You would have mass 1 times acceleration due to gravity times distance 1 plus mass 2 times acceleration due to gravity times distance 2. These are sine distances. Right? If these are balanced, then there's no torque, then they cancel out. Each one of these provides a moment about this point, and if they're equal, they cancel out, and then this fulcrum, this balance point, is at the center of mass. Otherwise, there's going to be motion. There's going to be rotational motion. So a teeter-totter does not really go up and down. It rotates. This person could fly off like that. So to calculate what I was trying to sketch out in the previous slide, we need a coordinate system. So we're going to pick a coordinate system. We're going to have two masses. One is going to be mass 1 and mass 2. They're got a balance beam. Forget the distance of the beam, and let's call this point x equals 0. Okay. So here is mass 1, and here is mass 2. And now I want to calculate the torque about x equals 0 provided by this first mass. The force associated with here, force 1, is going to be mass 1 times acceleration due to gravity. And let's call x1. That will give me the distance, the sine distance between the first mass and x equals 0. This is my first term, mass 1 times g times x1. For the other, I also have a torque here due to this mass. So the force 2 is mass 2 times the acceleration due to gravity. That gives me my first term, first factor in the second term. Now I need to find out how far I am from x equals 0, let's let that be x2. This is the total torque on the system. Now I'm going to factor out the acceleration due to gravity. What I'm left with is the moment. This is what's important in the center of mass calculation, the moment. You can forget about torque now and just look at moment by itself. Okay, and here's the definition of center of mass. If I calculate all the moments, I'll say all the moments, about some point x naught, and the sum of these moments equals 0, then x naught, or x bar rather, is the center of mass of the system. In other words, the system balances. I'm going to put that in quotes because you can't go too far with the word balance. The system balances at its center of mass. And that's shown here. We're going to derive this in a minute. So if this is the center of mass, then the torque provided by this weight, so let's say the torque 2, and here is torque 1, torque 2 plus torque 1 equals 0. But since I'm factoring out the g, which is constant to both, I will just have m1 x1 plus m2 x2 equals 0, and of course I can forget about the acceleration due to gravity. Before, the calculation was about x equals 0, and now I want to take this calculation about any value of x. So I need the distance from this force with mass m2, here's mass m1, about some point, and this point is going to be x bar. Well, say I have some kind of coordinate system here. Maybe the 0's over here. Then d2 is going to be x2 minus, oh, this is x bar, I'm sorry, minus x bar. Okay. d1 is located at x1. It's going to be x1 minus x bar. Again, these are not distances. In terms of a measure, they have sign. They can be positive or negative. So this is located at x1. Here's my x bar. This is the point where I'm taking the moment. It no longer has to be about x equals 0. It can be about any value of x. So d1 is x1 minus x bar, d2 is x2 minus x bar. The total moment is mass 1 times d1. So mass 1 times x1 minus x bar plus mass 2 times d2. So that's mass 2 times x2 minus x bar. If x bar is the center of mass, this is 0. We're going to use that requirement to calculate x bar. Okay, so here is the equation from before. m1 times x1 minus x bar plus m2 times x2 minus x bar has to be 0. Distribute m1 and m2 through the parentheses and collect terms, then factor out x bar and solve for it. X bar is m1 times x1 plus m2 times x2 over m1 plus m2. The numerator and the denominator have physical significance from what we've talked about before. M1 and M2 is the total mass of the system. That's the sum of the masses. Okay? M1x1 plus M2x2 is the moment about x equals 0. And so we've written that right here. X bar is the moment about x equals 0 divided by the total mass of the system.